quickly, this is just my little friendly reminder for the day. I don't know if you're aware, but we are having a modified schedule tomorrow, so we're not doing our regular Friday schedule. It won't be until next Friday that we actually get to experience the long period schedule. I'm looking forward to it. But tomorrow we're running the Liberty Time schedule, which is what we usually do on Tuesdays and Wednesdays. And there's going to be a pep rally at the stadium after 7th period tomorrow. So just like at the football stadium, because the first football game, I don't know, I'm not in charge of the decision making. I'm just sharing the information with you all. So anyway, that's exciting. Yay, go Bolts. Okay, also there is homework for tonight. Just want to let you know that. Bring your attention to that right now so that you are not confused. I made an executive decision as I was putting homework, like the calendar in, and I am totally bailing on the Canvas calendar already. So I hope that that's not going to like break anybody's heart. But it just isn't working for my brain already. I will try again if you guys want it and love it. But I think what I'm going to do instead is, and what I have done in the past, is that I put the calendar at the top of the unit. Does that make sense? So this is just how it works in my brain. If it isn't working for you, though, let me know. So if you click on the calendar, it'll open up and it shows you kind of what we've done and what we're doing. And then the homework is over here. Is that okay with everybody? So that's where you can find it if you want to know, or if you want to know what we're doing in the future. I didn't extrapolate all the way down for dates yet, but it'll get us through middle of next week. Okay, so that tells you what the homework is and all of that. I just want to make sure you know that, because I'm changing things from what I had initially planned. All right, so we're going to talk about the Buggys Lab for a little bit. We're going to do some definitions and start some problem solving today. So this is your opportunity, maybe the first time we've done this, to get your notes out. So you want to have a piece of paper out, something that you're ready to write on. For those of you that haven't had me in class before, the way that I generally roll, I'm not a PowerPoint person. I kind of do what I feel like are kind of organic notes. So I've got certain things that I want to talk about. But if you have questions at all during the time, you just let me know. We talk. It's great. Okay. So I had a couple of notes that I wanted to talk to you about as it relates to the Buggys Lab, the ones that you just turned in, and nothing that's going to, make or break a grade on anything, but just a few things that I want to make sure that we caught. And most of it has to do with best fit line. So I just want to talk a little bit about best fit line. We may have talked a little bit about this before. Come on, team. There we go. So the whole idea with the best fit lines, if you have these dots like this, okay, is that the best fit line needs to incorporate all of the data, right? So I know that in chemistry, you often would do this on a computer, and we also will do it on a computer, but the AP exam absolutely will have at least one question where you have the opportunity to plot data and then draw a best fit line. So I want to make sure from the get-go that you're ready to do that, okay? So when you're doing a best fit line, you're going to take your ruler, and you get a ruler on the AP exam. I will supply those to you, so you'll have your handy-dandy ruler, and then you have to kind of set it up and find a line that is close to balancing. Okay. Now, does it have to be perfect? No. I don't know who said yes, but the answer is no. It does not have to be perfect, but it needs to be reasonable. So when an AP grader is grading it, or when I'm grading a best fit line, I'm looking for something that kind of balances a little bit on each side. So something like that. Okay. If you have a data point that is obviously erroneous, like it's obviously an error or something that lived over here, then you can cross that data point out so that you get rid of it, so it's not a problem. Like this one, like see you later, it's not there. Okay, we don't need to worry about that one. But these ones here, we're going to kind of make that line happen. So a couple things about the line. These are things that you might want to write down in the graphing and best fit line section of your notes, if you so choose, would be that the best fit line will not necessarily go all through the points. You do not want to connect the dots. I've mentioned that before, but I want to make sure that you know, do not connect the dots. Not ever, ever, ever. Don't do it, okay? And the other thing that I want to make sure that you know, this example that I drew on the board is not a fantastic one, but you should never, ever force your best fit line to go through the origin, okay? Most of the time when we're doing a graph and we're taking data, it makes sense that there is a 0, 0 point, right? When we think about the bouncy ball lab that we did, goal 2, where you dropped it from a height and then it bounced to a height, It makes sense that if you drop it from a height of 0, it's going to bounce to a height of, like, that makes sense, right? But you can't actually take that data, so that means that you can't actually include that data as part of your data set. Okay? Same thing here. If you are, how far did it go every second? Well, at 0 seconds, it should have been at 0, right? Like, that makes sense. But again, you didn't actually take that data. That's not a piece. So there's not a dot here. So you never, ever want to force that best fit line to go through 0, okay? So do not force the line to go through the origin. Why not? Why don't you want to force it to go through the origin? Because you told us to? I mean, I suppose. Why don't you talk at your tables real quick? Why do you think maybe that it's not good science practice to force it to go through the origin? Have a conversation. What's that? What did you, oh, hello. There we go. Silly touch screen. What'd y'all come up with? Why is it not a great idea to force it to go through 0? I heard conversations, which means that there's great ideas out there. Yeah, go for it.
So like that graph right there is a good example. If you force it to go to the origin, it will miss the points and it's not going to fit as well as it could.
For sure. So if I was going to try and force it through the origin, and I'm still balancing, so like I'll get a couple of before, a couple of, on top and a couple below. Like, I mean, but what does that tell us? What does it do? I mean, I totally agree. Yeah, obviously it changes the slope for sure. What does that do in terms of the scientific, in terms of the science?
It makes it seem like there's a much sharper trend than what's actually.
Yeah, for sure. It gives you a very different value, doesn't it? If you're going to calculate a slope here, you're going to get a very different value than you would here. What do you think the y-intercept might mean? Let's talk about it in terms of the Buggy Lab. What did we have on the x-axis and what do we have on the y-axis for the Buggy Lab? Do you remember? I can't remember. Do you remember? Let's take a look. What do we put on the x? What do we put on the y? Time on the x and distance on the y. So if I have this value here, where at time equals 0, I have a distance that isn't 0, what might that tell you? What might that tell you? Yeah.
You did something wrong?
Yes! That's exactly right. Do you remember we talked about the very end of your labs in general, like when you're doing a lab write-up, and you are going to talk about your conclusion, you evaluate your lab and how well you did? If you use this blue line and have a very funny slope that doesn't really match your data, well, that may tell us, that may not give you the right information. Whereas this may have just said, oh, you made a mistake and there was something that was happening there. Like maybe you started your stopwatch too soon. Or maybe the person that was saying go, 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 go wasn't saying it quite at the right time. Or maybe the person putting the washers down wasn't putting them precisely down right where the buggy was. I'm sure that didn't happen to any of you. Oh, wait. It's a hard lab to do, right? Like, it was hard. There is error in there. And the fact that you have a y-intercept that is not 0, we think it should be 0. It makes sense that at 0 time it should have gone 0 distance. But the fact that you have a y-intercept that's not 0 tells us that there was some error in the lab. And you can even maybe figure out what happened as a result. Because you may have another graph, I'm not going to draw the data points out just for time's sake, but you may have another graph that has a slope like this, and so the y-intercept would be all the way down here. And the green graph, this one way down here, has perhaps a different cause of an error than the red one where the y-intercept is positive. Okay? So that value of the y-intercept and the fact that the y-intercept is not 0 indicates that there might be some error in the lab, in the process or the procedure. Okay, so why not? Because a non-zero, whoops, come on, silly thing, there we go. A non-zero y-intercept, not that y-intercepts always are 0, but much of the time they are. A non-zero y-intercept may indicate an error in the experiment. Hey, quick question. In chem, did you guys talk about different kinds of error? Did you talk about systematic versus random error? Did you guys talk about that at all? Okay, I'm just going to give these words to you. It's just good thinking here. Systematic versus random. If I'm ever writing up here and you can't read it because my handwriting gets terrible, just let me know. You're like, what does that say? Please let me know, because sometimes that happens. I want you to think about the Buggys Lab. I want you to think about what this word systematic might mean, what the word random might mean, and see if you can come up with an example of each. Somewhere where you might have seen that in your lab. Go ahead and do that real quick. Have a conversation. So systematic error versus random error. What did you come up with, friends? Systematic versus random. Either a definition for one of them, and it doesn't have to be a textbook definition. I'm going to tell you, I will probably not give you a textbook definition of anything this year. I mean, maybe once or twice if it's like a very specific thing, but usually it's just kind of from talking. So I don't want you to feel like you have to have it exactly right to say something, okay? We're working together, we're putting our brains together to get ideas of what these are. An idea of what either of these words might mean. Like, have you heard the word random before? Like, that's so random. What does that mean? Not in science, but in life. What does it mean to be random? Do you guys really not know? Or are you just like staring at me? Spontaneous! Yeah, spontaneous. How often does something that's random happen? Like, I mean, like a specific thing. Does a random thing happen all the time?
Your screen's frozen.
Oh no, you can't see all of my pretty orange lines. There you go, bam. Now you can see them. See, they're pretty, right? Yeah. Line, arrow. Random. Do random things happen a lot? Or is it like just a one-time deal?
Maybe.
Yeah, I mean, a specific random thing, right? Like, if something keeps happening over and over and over, would you then keep calling it random? Probably not, right? I'm trying to think of something that would be, okay, I got one for you. So my husband grew up in Davenport, near the river, right, Mississippi River, and he was playing outside one day with his dog. I don't know, they were playing, this was like a little kid. And all of a sudden, a fish fell from the sky. Right? Question, is that systematic or random? Totally random. It was like, what the fish? Right? He looked up and there was an eagle that it was flying and it accidentally dropped. It was from his talons, right? Like, it makes sense once you're like, oh, okay, yeah. That was random. Now, if he kept, playing outside every day and every day a fish kept falling from the sky, I mean, probably not going to happen, but you never know. Then, not so much random anymore. So random means Like kind of all of a sudden accidental one-time deal, right? Okay. So we'll just say, I don't want to say that. I don't know. Not predictable. Okay. Maybe single occurrence. Often when I put two words up there, they're opposites, right? You may have gotten that sense. So if something's not random, it's systematic. What does that mean? What's that? It's predictable. It happens over and over and over. I like that you said predictable since you said not predictable. Is that where that came from? I like the way you think. That's awesome. Yes. Predictable. It happens all the time, right? It happens over and over. Okay. We're talking about errors, things that go wrong. Wah, wah. They both exist in labs all the time. Can you think of an example when you were doing your Buggy Lab yesterday of a random error, something that happened, not predictably, single occurrence, one-time deal? Something that happened that wasn't supposed to happen? No? Anything bad? Yeah, go ahead. Forgot to turn on the buggy. Absolutely. That would be a random error, right? Now, that one probably you didn't like sit there and measure data for it. But yes, that's absolutely true. That would be a thing. That would be an error in process that isn't going to happen over and over, I hope, because if it did, that was like, then we'd have a fundamental problem, right? Yeah, absolutely. So misuse of equipment, right? But it's just like a one-time deal. One-time deal, absolutely. Other random errors that you can think of? Yeah.
When we chose our path, after about 4 seconds, the buggy would run into something, usually into one of the desks.
Oh, yeah, so that probably wasn't the best path, right? Like, oh, yeah. So then you kind of fixed it and you did another one. Is that true? Yeah, absolutely. How are you taking data? What were you doing in order to collect data for the buggy moving? What were you putting down? Washer after washer after washer. Anybody have a hard time with like putting washers down sometimes?
Yeah.
Maybe like tripping over your lab partner, like tripping over a chair, something like that. Right? So like maybe like you had nice washers and then whoa, and then another one that was good. Right? That would be a random error. Random occurrences. Okay? A random error is going to cause that kind of thing to happen. Okay? A random error will cause an outlier. Okay? And random errors can be minimized. How? What do you do to kind of get rid of random errors? Like this goofy one here. Yeah. Yeah. Do more trials, right? More trials, more data. Do more trials. Or collect more data. Absolutely. That's fantastic. So that's one way to get rid of those things. Systematic errors. Those are things that are going to happen over and over. So it says predictable. I worry about that just a little bit because I don't want you to think that it makes it okay, right? But I'm saying that something that's going to happen over and over and over again. What kind of errors do you think might happen over and over and over again? Can you think of anything that might have happened? Yeah.
Like the person saying the time, like, wait, I just need time.
Absolutely. Yeah, so they're doing the same thing. They're just doing it wrong. Right? So systematic errors are going to result in just all of the data being off by a little bit. All data is off by the same amount. And because it's all off by the same amount, you might not know until after you've taken all of your data. Because it all looks like it's following a pattern, it's just that the pattern isn't quite right. Okay? You can't really fix that by doing more trials because all the trials are being screwed up. But systematic error can be fixed if you are careful about your procedure, right? So I'm going to say pay attention to the procedure or plan. Okay. Which kind of error, systematic or random, causes this to happen? She whispered it. So I said, say it loud, and she said, like in this voice. Say it loud! What did you say? Systematic! Yeah! This is a systematic error. Okay? That's what we're talking about. This thing right here. Systematic! Awesome. Okay. Fantastic. All right. That was not on my list of things to do today, but it's an important thing to do, so I'm glad we did it. Good for us. We had to do it at some point, so it's a good day to do it. All right. Questions on this before we move on? Okay. After you graphed your data, you plotted your data. Bam, 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 bam. You drew your best fit line. Maybe something like this. Then what did you have to do next? I heard lots of people speaking very quietly. I couldn't hear you. Say again. Find the slope. Absolutely. A couple notes about finding the slope. This is super important. Okay? When you're finding the slope, use points on the best fit line that are not data points. Even if your data points are on the line. That seems a little weird. And I always have students that are like, but if they're on the line, it's okay, right? The answer is no. Okay? There are some statisticsy reasons why that's really not okay. So the game is to find 2 points that are on the line that are not your data points. Okay? Generally, the way that I do this, and if you didn't do this way, for the lab that you just turned in, it's all good, because you didn't know, right? We're talking about it now. So from here on out, you know that when we're doing that, we're going to find a point over here. I usually put X's through them. Okay, you'll have to do that on stuff for tests and quizzes and things. X's through them, and then find the coordinates of those points. Find the slope between those 2 points, okay? I would also strongly encourage you, again, from a statistics point of view, to pick points that are far away from each other, not because you get a different slope here versus here, but because it's easier to read and make sure that you're getting good values than if you pick 2 that are very, very close together. Does that make sense? Okay, so pick 2 points that are far apart from each other and find the slope. Oh wait, how do we find the slope? Slope is marked with the letter M, right? Anybody know why that's true? I don't have a fun fact to tell you why. I really don't know. I'd like to know. Somebody can tell me that. I'd be very interested. Find the slope. It's M. How do you find it? Say it. You want to say it? For sure. Y2 minus Y1 over X2 minus X1. I usually will write that as delta Y over delta X. Are y'all familiar with delta? You met delta before? 4th letter of the Greek alphabet. It's right up there. Alpha, beta, gamma, delta. Yeah. Delta means what? Change in. So you've got change in Y over change in X. Delta. Change in. Yeah. What are your Y values in this case? We had what? Time on the x-axis down here. And we had distance over here. So delta Y, the description of delta Y is going to be what? Distance, time, something else? Change in Y. Delta y is measuring what? Distance. Delta x is measuring time. And the first analysis question, I think it was, says, what does the slope of the graph represent? And what did you say? Speed. Sure. Or maybe you said velocity. Either one of those is okay with me because we haven't really parsed which one is which. Are we okay? Yeah? Issues, questions, or concerns right there? Why do we do this? So that we could learn how to find speed on a graph. Right? Happy? Good again? Cool. I'm just rocking. I just want to make sure how much time I have left. Fantastic. 10 more minutes. I love it. All right. Somebody, can't remember if it was this class or the class, asked me a clarifying question yesterday, and I want to clarify that with you today. It has to do with speed, distance, and time, and we'll define those a little bit more in just a second. But before that, we have 4 words. The words are distance and displacement, speed and velocity. What? Oh, the like do. What are you doing? Sorry. Do you guys know if there's any differences between the top 2 or the bottom 2 words? Yeah? Velocity is speed in a given direction. Have you guys done this in math already? Or did you do it somewhere else? Science. What science class did you do it in? Cool. Awesome. That makes me really happy. Last year, I assumed that everybody knew this, and I was like, what? When they were like, I don't know. So that's why I'm asking. Velocity is speed in a given direction. Speed is how fast something's going, right? How much distance it covers over time. Does anybody know a difference between distance and displacement? Or do they sound like they're the same thing? Yeah.
Displacement would be like how far it is from the start to the end, and then distance is how far you traveled in that way.
Absolutely. Absolutely. So I think I was kind of watching your hands act that out. So I'm going to see if I can draw what you were kind of doing there to see if I'm understanding what you said. So if here's point A and here's point B, and one person walks like this and another person walks this path, right? I mean, everybody does their own thing, and that's awesome. We respect that and we love that. Okay? So let's label them. Well, are we okay with colors? If you're a person that does not do color, and I don't say that in a making fun sort of way, my husband is color deficient, and so it's hard for him to see things. So if that's not making sense, you just let me know so that I don't refer to color all the time, because I love color. So I'm going to talk about green and blue, but give me a wave if that's like a bad thing, or come talk to me after class. So this one's the green one. This one's the blue one. Okay. Which one traveled further distance? Blue, right? Okay. If you look at their step counter, the person that went the blue route got a lot more steps in. Okay. Whereas the person that followed the green route did not get a lot of steps in. Who has bigger displacement? Same. Okay. So distance is like the number of steps. Obviously not only number of steps, but that's a nice kind of way to think about it, right? Number of steps along a path. Whereas displacement, it does not matter how you get there. It does not matter, okay? It's only a change in position. So if you think about your day, and I don't know what time you wake up or go to bed, but I'm going to have a positive thought process and assume that you all get up at about, 7, 6, we'll say 7. Just, like be on a late day, we'll say. And let's say that you all go to bed at 10, right? I'm sure that happens for everybody, right? And I'm assuming that, I'm making a lot of assumptions here. I'm assuming that you sleep in the same place day after day after day. If that is not the case for you, that's fine, and I'm not judging. But let's assume that for someone, they go to bed at 10, they get up at 7. I want you to think about their day, okay? Tell me about their displacement from 7 a.m. and then to 10 p.m. that night. 0. Their displacement is 0 because they start and end in the same spot. That doesn't sound like it's very impressive because they may have traveled a whole long distance, but the fact that they got there to the same spot means their displacement is 0, okay? In physics, we generally focus on displacement and velocity, okay? Velocity is speed in a given direction, and the direction part will matter soon, but for now, they're kind of interchangeable, okay? Like until maybe tomorrow, okay? Speed is distance over time generally, though. Whereas velocity, the one that we're going to use a lot, is marked with a V and is equal to delta x, that's displacement, change in position, x is position, okay? Velocity is delta x over time. So even if you did a whole lot of stuff during the day, if your change in position is 0, then your velocity is 0, right? 0 divided by anything is 0. Units real quick. What are the units of change in position? What do we measure position in? I heard some like grumbles of something. What? Kilograms? Newtons? What are we measuring position in? You guys measured position yesterday. What units did you use to measure position or distance? Centimeters or meters, right? The base unit is meters. Time, base unit, what are we going to use? Simplest one is seconds. Velocity, the units are, it's literally right there. It's like staring you in the face. Velocity's units are going to be, bam, it's easy. It's easy stuff. Meters per second. How are we doing? We okay? Okay, I love it. I love it. All right. We are going to do, let's see. We're going to do a problem quick just because I want to make sure that you're exposed to this problem-solving business. It's a pretty easy problem to start with. Easiest problem we're going to do all year. We're going to start right now. I tell you what. I'm going to let you just go at it. Go at it. We'll talk about the proper way to do it tomorrow. See if you can solve this problem. Kermit, yes, the frog. The huge Muppets fan. I feel it is my goal as a child of the 80s to share the Muppets with you all because I feel like it's a cultural experience that everyone needs. How far does Kermit walk if he maintains a speed of 1.5 meters per second for 2 minutes? Give that a try. Give that a try. See if you can get it.